Inverse optimal control aims to learn the objective function of a nonlinear optimal control system from its states and inputs. However, this task is challenging when the system dynamics are unknown. To address this issue, a data-driven approach is proposed, leveraging the deep Koopman representation of the unknown system. This representation employs a deep neural network to represent observables for the Koopman operator, which has been used to represent unknown nonlinear systems by linear time-varying systems. The approach assumes the objective function to be learned is parameterized as a linear combination of features with unknown weights. By doing so, it learns the Koopman representation of the unknown dynamics and the unknown weights in the objective function together. This is in contrast to existing inverse optimal control methods, which typically require knowledge of the system dynamics and parameterize the unknown objective function as a linear combination of selected prescribed features. These methods often incur high computational costs and require complete demonstration data. The proposed approach does not require information on system dynamics and can learn the objective function and dynamics model from demonstration data. This is achieved through an iterative learning framework, where the Koopman operator and the control objective function are learned simultaneously. By doing so, the approach can develop a method that learns the control objective function and the dynamics model from demonstration data, without requiring exact knowledge of the underlying system dynamics. This data-driven approach has the potential to overcome the limitations of existing inverse optimal control methods and provide a more efficient and effective solution for learning objective functions in unknown nonlinear systems. The paper addresses the problem of data-driven inverse optimal control, where the goal is to estimate the unknown weight vector in the control objective function using a given dataset of observed state input sequences, without knowing the system dynamics. The system dynamics are modeled using a discrete time optimal control system, where the unknown dynamics are denoted by f, xt, ut, and the control objective function is a linear combination of known features and unknown weights, denoted by j, x0, t, u0, t. A set of observed sequences of states inputs, denoted by d, is given, where each sequence is a segment of a system trajectory that minimizes the cost function j. The goal is to develop an algorithm to estimate the unknown weight vector, using inverse optimal control with the given dataset d, without knowing the system dynamics. The paper employs the deep Koopman representation to approximate the unknown dynamics. The deep Koopman representation uses a nonlinear mapping, parameterized by, to approximate the unknown system dynamics. The mapping is represented by a deep neural network with a known structure but unknown parameters, which are determined by the set of observed trajectories d. The paper then presents the data-driven inverse optimal control algorithm, where the objective function and the Koopman operator dynamics are jointly learned. The algorithm approximates the unknown dynamics using the deep Koopman representation, and then uses the approximated dynamics to estimate the unknown weight vector. The dynamics approximation loss is defined as the difference between the estimated states vector obtained by the deep Koopman representation and the actual states vector. The C matrix is computed by minimizing the dynamics approximation loss. The data-driven inverse optimal control (IOC) algorithm is a novel method for estimating the unknown objective weight in system dynamics, utilizing a given dataset of observed sequences of states and inputs. This is achieved through the iterative update of the parameters of the Kung style, the time annotated, and the matrix C, which are essential for the approximation of the system dynamics. The process is based on the use of a deep neural network, Dual Rigali, 2019, which is used to generate the initial value of the parameter and the initial value of the matrix C. The process is then iterated with the use of the dataset, which is used to update the parameters of the model. The process is then repeated until the convergence of the model is achieved. The convergence of the model is ensured through the use of a series of lemmas, which demonstrate that the estimation error, which represents the difference between the approximated and true system dynamics, converges to zero under certain conditions. These conditions include the use of an infinite number of hidden layer nodes in the DNN, a sufficiently small observation interval, and the condition that the maximum error in the observable function is zero. The process is then used to solve the data annotated IOC problem by first initializing the Kung style using the DNN with an initial guess of the parameter. Then, it iteratively updates the Kung style and the matrix C using the dataset, solves for the parameter, generates the matrix, and finally solves for the least square estimate of the weight vector. The process is then repeated until the convergence of the model is achieved. The process is based on the use of the following steps. 1. Initialization of the model using the DNN with an initial guess of the parameter. 2. Iterative update of the parameters of the model using the dataset. 3. Solving for the parameter. 4. Generating the matrix. And 5. Solving for the least square estimate of the work. The process is then repeated until the convergence of the model is achieved. The process is based on the use of the following notations. Is the parameter of the model, is the matrix of the model, is the time annotated, is the time annotated, and is the time annotated. The process is then used to solve the data annotated IOC problem by first initializing the model using the DNN with an initial guess of the parameter. Then, it iteratively updates the model using the dataset, solves for the parameter, generates the matrix, and finally solves for the least square estimate of the work. The process is then repeated until the convergence of the model is achieved. The process is based on the use of the following notations. Is the parameter of the model, is the matrix of the model, is the time annotated, is the time annotool, and is the time annotool. The process is then used to solve the data annotated IOC problem by first initializing the model using the dual with an initial guess of the parameter. Then, it iteratively updates the model using the dataset, solves for the parameter, generates the matrix, and finally solves for the least square estimate of the work. The process is then repeated until the convergence of the model is achieved. The process is based on the use of the following notations. Is the parameter of the work, is the matrix of the work, is the time annotool, is the time annotool, and is the time annotool. The process is then used to solve the data annotated IOC problem by first initializing the model using the dual with an initial guess of the parameter. Then, it iteratively updates the model using the dataset, solves for the parameter, generates the, and finally solves for the least square estimate of the work. The process is then repeated until the convergence of the model is achieved. The process is based on the use of the following notations. Is the parameter of the work, is the matrix of the work, is the time annotool, is the time annotool, and is the time annotool. The process is then used to solve the data annotated IOC problem by first initializing the model using the dual with an initial of the parameter. Then, it iteratively updates the model using the dataset, solves for the, generates the, and finally solves for the least square estimate of the work. The process is then repeated until the convergence of the model is achieved. The process is based on the use of the following notations. Is the parameter of the work, is the matrix of the work, is the time annotool, is the time annotool, and is the time annotool. The process is then used to the by first initializing the model using the dual with an of the parameter. Then, it iteratively updates the model using the dataset, solves for the, generates the, and finally solves for the least square estimate of the work. The process is then until the of the model is. Theorem 1 establishes the convergence of estimated system dynamics and the weight vector to their true values. The difference between estimated and true partial derivatives is defined as equals, and it is shown that this difference converges to zero as the norm of the estimation error Ketke approaches zero. A similar convergence is demonstrated for the difference between estimated and true partial derivatives with respect to the control input ut. The proof involves constructing a matrix F with data, where F equals ff, and F is a matrix containing the differences between estimated and true partial derivatives. This matrix is used to derive an equation that relates estimated system dynamics to true system dynamics. Specifically, the equation is used to establish the convergence of estimated system dynamics to true system dynamics under certain conditions, namely when the norm of the estimation error is zero and the observation interval t is sufficiently small. The proposed data-driven inverse optimal control algorithm is evaluated using a simulation of a pendulum model, described by the continuous time dynamics equation, 43. The equation is discretized to obtain a discrete time model, 45, which is used to simulate the motion of the pendulum and evaluate the algorithm's performance. The algorithm learns the weight vector and system dynamics F from segment data of the optimal trajectory. Simulation results in Table I and II demonstrate the effectiveness of the algorithm in learning system dynamics and the weight vector from data. The two-norm error between estimated and true weight vectors is used as a performance metric. The results show that decreasing the maximum value of the regularization parameter Lmax_c and increasing the number of hidden layer nodes nh improve the algorithm's performance. The algorithm is able to recover true system dynamics and weight vectors, even in the presence of regularization and limited data. Equations 32 and 42 are used to derive the relationship between estimated and true system dynamics. Equations 35 and 36 establish the convergence of estimated partial derivatives to true partial derivatives. Equations 39, 40, and 41 define the matrices A, B, and V, used to construct the matrix F equation. 46 defines the objective function used in the simulation to evaluate the algorithm's performance. A data-driven approach is presented to solve the inverse optimal control problem with unknown system dynamics. The finite-dimensional Koopman operator is employed to approximate the unknown system dynamics, where observables are represented by a deep neural network. The regularization parameter, Lmax, significantly affects the accuracy of the inverse optimal control results. Decreasing Lmax from 1e4 to 1e6 yields a lower error of the weight, resulting in a reduced 2 norm of the error between the ground truth trajectory and the trajectories produced using the estimated Koopman operator. This suggests that as the error of the weight decreases, the approximated trajectories become more accurate. The architecture of the deep neural network also influences the accuracy of the inverse optimal control results. Increasing the number of hidden layer nodes from 1254 to 2086 leads to a decrease in the error of the weight, resulting in more accurate approximations of the trajectories. This demonstrates that as the error of the weight decreases, the 2 norm of the error between the ground truth trajectory and the trajectories produced using the estimated Koopman operator decreases, implying convergence of the approximated trajectories to the true trajectories. An iterative scheme is proposed to update the least square estimate of the weight vector in the unknown system dynamics. This approach enables the estimation of the weight vector and the generation of optimal trajectories using the estimated Koopman operator. The method assumes perfect data, which is often challenging to fulfill in reality. Future research directions include extending the proposed method to accommodate noisy data and performing inverse optimal control with system output rather than states. Connections to existing literature in the field of inverse optimal control and Koopman operator-based approaches are established, highlighting the potential of this data-driven approach for solving inverse optimal control problems with unknown system dynamics.